Hello everyone. At today's meeting, we will tackle the most important architecture proposed in the subject of natural language processing in the last 6 years. An architecture that has marked a new era in NLP, but also an architecture that is quite hard to understand because there is a lot going on. In today's lecture, I will talk about the transformer architecture, trying to make this idea as easy to understand as possible. Moreover, I will describe the attention mechanism, which is a little bit older than the transformer, but is a really related concept. If you haven't watched the previous lectures, I highly recommend watching them before watching this video, as today's lecture is the continuation of the previous ones. Let's start our journey with an outline of today's lecture. First, we will do a quick recap on the previous lecture and discuss the drawbacks of the recurrent neural networks. Then, we will introduce the idea of attention, which addresses one of the most important limitations of RNNs. In the second section, we will provide a general overview of the transformer architecture, which tells us that we can process sequences without using recurrent connections, because, as the title of the paper introducing transformers says, attention is all you need. The internals of the discussed architecture are quite complex. We will first describe the input that we send to the network, which are static word embeddings enriched with something called positional embeddings. In the next section, we will introduce the idea of self-attention, which is the core component of transformer. Then we will iterate over each building block of both the encoder and the decoder. Yes, the transformer architecture is indeed an encoder-decoder neural network. Finally, we will compare transformers to different architectures, especially those providing static word embeddings, like word2vec, and those providing contextual word embeddings based on recurrent neural networks, like ELMO, which we discussed during the last lecture. There's a lot to discuss, so let's start. At our last meeting, we looked at how we could generate context-aware representations of the meanings of words, or tokens in general, based on the outputs of the hidden layers in RNNs trained with the language model objective, or in other words, trained to predict the most probable next token in a sequence. These contextual representations were required especially for words of which the meaning is context-dependent, like the word book, which might refer to a physical book or the process of booking, or in the case of the pronoun it, which might refer to anything. We call such words polysemic. However, the results achieved by architectures such as ELMO showed us that such context-aware representations can easily generate state-of-the-art solutions for a variety of tasks. So these representations might be also useful not only in the context of polysemic words, but also in the context of all words that we encounter. However, there are two major drawbacks of recurrent neural networks that are caused by their nature. First, they need to process the sequence step by step, because we need to calculate the output of the previous hidden layer to calculate the output of the current hidden layer. Second, they model the meaning of the whole sequence in a single vector. In the case of short sequences consisting of, for example, 10 tokens, and extremely long sequences consisting, for example, of 10,000 tokens, the representations of the sequences can be extracted from the output of the last hidden state, and this is a single fixed size vector. The consequence of the first drawback is obvious. We cannot parallelize the training in the context of a single sequence. But what's the consequence of the second drawback? Let's consider a simple recurrent neural network cell which calculates the value of the hidden state as the sum of the static word embedding vector representing the current word, for example the word like, and the output of the previous hidden layer, the output of the hidden layer at the time step t-1, which is transformed using an appropriate matrix representing the recurrent connections. We called this matrix V during the last lecture. At the first time step, the information stored in the hidden state is entirely determined by the current static word embedding related to a given word. We mark it using the same color for a current token and the information stored in the hidden state. However, processing the second token, during the second time step, the value at a hidden layer will be a mix of the current static embedding and the output of the previous hidden state. So 50% of the information comes from the current token, in this context the word like, and another 50% of the information comes from the previous token, in this context the word I. It's even more interesting during the subsequent steps. In the final step, after selecting the static word embedding for the period, we sum that representation with the previous hidden layer's output that is transformed using the V matrix. Similarly to the previous case, 50% of the information represented in this hidden layer comes from the current token, the period. However, the previous hidden state is already a mixture of the meanings of a sequence of words. In the previous hidden layer, 50% of the representation comes from the token assigned to this time step, the token NLP, while the remaining 50% from the previous sequence, which models both the words I and like. The final hidden state thus consists of a mixture of meanings but is dominated by the most recent tokens. 50% of the information comes from the period character. 25% of the information comes from the NLP and 12.5% comes from the word like, which is the same amount of information as in the case of the token I. The longer the sequence is, the less information about first elements of the sequence are preserved. Some solutions to this might be using some more advanced recurrent neural network cells like LSTMs or GRUs, but they don't solve the problem completely. This problem is particularly troublesome in the context of machine translation. Imagine that you are going to translate a paragraph of text starting with I like NLP into another language, let's say German. This can be achieved using encoder-decoder architecture, in which the encoder encodes the information about the whole input sequence, the paragraph starting with I like NLP in English. Here we have only in the sentence I like NLP to simplify the visualization. And then the decoder uses the last hidden layer's output to generate a sequence of tokens in the target language, here in German. So here we generated a single sentence in German starting with Ich mag NLP. In order to produce the first token of the translation, the model needs to reach the first token in the input sequence, because the translation of the word I in German is the word Ich. However, the model can only access the last hidden layer, which is a mixture that represents the first token only in a small fraction. Assuming even short input paragraphs representing the text in English to be translated into German that consist of, let's say, 10 tokens, using vanilla RNNs, the information in the last hidden state will consist only in 0.2% of the first token. And as you might expect, this is a huge problem, because that final encoder's representation will be dominated by the last tokens in the sequence. These big distances between related tokens are called long-range dependencies. A possible solution was proposed in 2014 when Dmitry Bagdanov and others introduced the idea of attention in the paper entitled Neural Machine Translation by Jointly Learning to Align and Translate. The general idea here is quite simple. Instead of accessing only the last hidden layer state to produce a given output, for example the word ish, let's access all the hidden layers outputs at each time step and calculate the importance of them for our current step. Then we can construct a representation that will consist of the most important pieces of information. So how can we do this technically? Let's extract the hidden layers outputs from the encoder at each time step. In this example presented on the slide, we obtain 4 representations, 4 contextual embeddings, each of which represents the meaning of a given token in the context of the previous sequence. Each representation is marked with a red rectangle. Then, on the decoder side, we work in the context of a given token. Let's capture the representation of the decoder's input at a given time step. For that purpose, we use its static embedding, represented here using a green rectangle marked with Q1 sequence. In order to produce the first token in German, we may utilize a special BOS token, which means the beginning of the sequence, as an input, which tells us, hey, we need to start generating. But what information from the input sequence is the most important now? We know that in order to produce the word ish, we need to focus the most on the word I in the input sequence. We need some measure that can provide us with the information about the importance of each encoder state in the context of a given decoder state. If we ensure that both the encoder hidden states, here H1, H2, H3 and H4, and the embeddings of the decoder inputs, here Q1, are of the same length, we can easily measure the importance in terms of the similarity between these representations. We can simply calculate the dot product between Q1 and each of the H1, H2, H3 and H4 vectors. The similarities calculated using the dot product can be any numbers from -infinity to +infinity. Let's normalize them using softmax, so that all similarities will be between 0 and 1. And the sum of all similarities calculated will be always equal to 1. Now, these numbers can be interpreted. We can treat those values as the importance scores. From now on, we call these values attention weights. As we can see the similarity between the first decoder input, an embedding representing the BOS token, and the embedding H1 related to the token I sent to the encoder is the highest. Its value after softmax is equal to 0.984, so considering the maximum achievable value after applying softmax is 1, the similarity is really high. You might wonder how those scores can be meaningful. Remember that those representations, those embeddings, are learned during the training process using backpropagation. If we provide the network with enough data, the network will learn that it's beneficial to generate such representations that will be similar for pairs of words that are related between the encoder and the decoder. We give the network some possibility and it can learn to use it. If the network learns that for the decoder state Q1, the most important encoder state is H1 related to the first token, we can try to construct a new representation of the whole input sequence that will be dominated by the first encoder's embedding, H1. In machine learning, we like fixed length representations so that they can be added or concatenated with other vectors. For that reason, we construct our context vector as the weighted sum of all the hidden states H1, H2, H3, H4 from the encoder, weighted according to the attention weights calculated. As we can see on the slide, the resulting vector is dominated by the most important token from our perspective, the token I, which gives us almost 99% of information in this vector. The resulting vector will be always of the same size, regardless the input sequence length. It is always equal to the encoder hidden layer dimension because it's a weighted sum of hidden layer outputs at different time steps. Finally, we can concatenate the decoder's input representation, the static embedding Q1, with the calculated context vector V1, so that it can help produce the output. And now we can deal with long-range dependencies, as we can access all the encoder states and choose which are the most important from our perspective for a given decoder state. However, please remember that this increases the memory needed to use such network. Instead of remembering only the last hidden layers output in the encoder, we need to remember all hidden layers outputs produced by the encoder. Here in this slide, we can see the concatenated vectors used to predict the first token ish in the generation and the decoding phase. The paper Neural Machine Translation by Jointly Learning to Align and Translate, the link to which can be found at the bottom of the slide, provides some interesting visualization of the attention weights. Here, we have an image representing the translation from English to French. For each French word to be produced, a given row represents the attention weights over all tokens processed by the encoder, over all English tokens. Those attention weights are presented using a matrix, which we call attention matrix. We can see here that most of the corresponding words in English and French are located in the same positions. Then translation of the token "the" is also the first token, and we can see it in the attention matrix, as in order to produce the first token in French, the attention mechanism focuses especially on the first token in English. The brighter cells are those with high attention weights, and darker cells represent those cases where the attention weight is low. For instance, from the perspective of the second token in French, the attention weight related to the word agreement is really high and probably close to 1. However, for instance, the token August is completely unrelated. The value of the attention weight is close to 0. We can see that the French translation of the phrase European Economic Area changes the order of words, and this can be spotted easily using attention matrix. In subsequent years, some modifications of the way we calculate attention weights were proposed. Instead of calculating the dot product, we can introduce a new matrix, learning some linear transformation during the training process. We call it multiplicative attention. We can also utilize even more complex operations, as in the case of additive attention, introducing some nonlinearities like applying the hyperbolic tangent function. We can also decide whether we want to use all the encoder states to generate the context vector. We call that case soft attention or global attention, or whether we want to select only the most important encoder state and use only it as the context vector. This scenario is called hard attention. Alternatively, instead of using only the most important encoder state, we can also create a window of a given size around that most important state and create a context vector based on the weighted sum of the encoder states inside of this window. This scenario is called local attention. In the rest of today's story, we will use the dot product as the similarity measure and the global or soft attention that takes into consideration all the encoder states. Understanding attention is crucial to understand the main character of today's story, the transformer architecture. At the beginning of this lecture, we stated that recurrent neural networks have two major drawbacks. They represent the whole sequence using the last hidden state, and we just learned how to deal with it using attention. And also they have to be processed sequentially. This obstacle was much harder to be addressed. However, in 2017, a huge breakthrough was proposed. Ashish Vaswani and others published a paper that changed the future of NLP. The paper, entitled "Attention is All You Need," proved that we can get rid of the recurrent connections that are used in recurrent neural networks and still process sequences. But this time, we can do it much more effectively, because we don't need to compute our output sequentially, we can parallelize our computations. The link to the paper "Attention is All You Need" can be found at the bottom of the screen. However, beware, this one requires much more time to understand it than the previously linked ones. There is even a Polish accent here. Łukasz Kaiser, who works at Google, was a co-author of this paper. Łukasz is also an instructor who teaches natural language processing on the Coursera platform in the natural language processing specialization, the link to which you can find at the bottom of the screen. This is a great course focusing on various aspects of natural language processing. The overview of the transformer architecture is presented in this image. The image comes from the "Attention is All You Need" paper. Transformer is an encoder-decoder architecture where the encoder learns to produce some vector representation of the input sequence, while the decoder tries to use that representation to produce the output sequence. The transformer architecture was evaluated mainly on the machine translation task, where it was used to generate translations from English to German and from English to French. But the authors showed that it's also useful in the context of tasks such as constituency parsing. The implementation details of the transformer architecture are quite complex, so we are going to dissect it into smaller parts and understand them one by one. The most demanding ones will be the concept of self-attention and the idea of positional embeddings. Let's start our story with the encoder's description. In the first step, the encoder obtains a sequence of words, or tokens in general, represented using one-hot encodings. These might be, for example, tokens representing English words to be translated into German. It's the same idea as discussed in our previous lectures. Because our one-hot encodings can be used to retrieve a given row or column from a matrix called embedding matrix, we simply transform one-hot representations into static embeddings, representing the meanings of words independently from its context. The embedding matrix is learned with the whole model. What is important here is the fact that we can process each token in parallel, transforming all tokens passed to the encoder into word embeddings at the same time. Then we encounter an additional building block called positional encoding. In a moment, we will learn that the subsequent transformations cannot model the order of words because they do not use the recurrent connections. For this reason, we need to somehow inject the information about a given position to our static word embeddings so that we will not only represent the meaning of a given token, but also its position in the sequence. So let's think about it. We have a set of static word embeddings related to our input sequence of a given length. For example, the sentence in English that we want to translate into French that might consist, for example, of 10 tokens. What could be the easiest approach to take to inject the positional representation? Theoretically, we could add a vector to our static word embedding that has all values set to the number representing the position of a given word. For example, we add the vector of zeros to the embedding related to the first token. Then we add the vector of ones to the embedding related to the second token. Then we add the vector of twos to the embedding related to the third token, and so on. We could obtain new embeddings preserving the same length that are position aware. Great, isn't it? Well, no. There are at least two problems with such an approach. First, we train our network on a given training set. This set won't cover all the possible lengths. As a result, when using such a trained model to predict the outputs, we might encounter a situation in which the sequence will be so long that the values in the embedding vector will be much higher than those observed during training. However, there is even a bigger problem here. Large positional embedding values assigned to the final tokens in long sequences will make the training process unstable, as the gradients will become large. The neural networks prefer vectors with values that are closer to zero. We need to find a better solution that won't produce values that big. A second similar idea might be not to use integers representing positions as the positional embedding values, but to normalize them, dividing each positional embedding value, generated as described on the previous slide, by the length of our sequence. This way, the values won't become bigger than 1, so that we mitigate the problem of unstable training. Indeed, this is a better solution, but it also has its drawbacks. The biggest drawback related to it is the fact that the intervals between values will mean different things depending on the sequence size, and the network won't be able to learn a meaning from this. Consider, for example, two sequences of words. One that contains 10 elements and one that contains 1000 elements. The increase of 0.1 in value of the positional embedding content in the second context represents a difference of 100 words, because 10% of 1000 is 100. A difference of that size represents the process of moving forward by 100 words, while in the context of the first example, the same difference represents the process of moving forward by only one token. As we can see, we cannot easily generalize the knowledge about the differences between positional embedding values. For each sequence length, a given delta, for example 0.1, will mean something different. Because such basic approaches failed, the authors of the transformer architecture developed an alternative form of representing positional embeddings that will ensure that the values at each position will fall into a given range, and the interpretation of the difference between two values in a positional embeddings will be meaningful regardless of the input sequence size. The authors of Transformer utilized the same idea of adding the positional representation to a given static word embedding. However, now those positional embeddings are generated in a, let's say, more advanced way. A way that allowed us to meet the following criteria that are listed on a website presented on this slide, which contains a great description of the idea of positional embeddings used in Transformer. So the method producing positional embeddings should output a unique encoding for each time step. Distance between any two time steps should be consistent across sentences with different lengths. Our model should generalize to longer sequences without any efforts. Its values should be bounded to some value range. And finally, the method producing positional embeddings must be deterministic. We see that we need our values to be bounded, so maybe we could apply some sigmoid function to ensure that the values are between 0 and 1. Or maybe some hyperbolic tangent to make it between -1 and 1. Well, the problem is that the variability decreases quickly as the argument of the sigmoid or hyperbolic tangent becomes very large or very small, and it does not provide a consistent distance between any two time steps. For this reason, the authors used periodic functions, the sine and cosine functions. However, it's not that easy to choose appropriate frequencies of this. Setting them too high, the values will repeat among our sequence, so the embeddings, the positional embeddings, won't be unique, while keeping them too small will introduce small differences between the positional embedding values of the adjacent positions. If we compare such adjacent positions, adjacent tokens, we won't be able to capture such small nuances when comparing those representations. For these reasons, the authors decided that each of the values in the positional embedding vector should obtain a different value instead of setting the content of the whole vector to the same value. In these positional embedding representations, even positions used sign functions to calculate values, while odd ones used cosines. Moreover, the frequencies of those sines and cosines decreased along the embedding dimensions, so that instead of deciding which frequency to use, let's use many of them at once. Using multiple frequencies is related to encoding a given integer in the binary format. If we look at the binary representations of the first 16 numbers from 0 to 15, we can see that the frequency of changes between the bit values is the biggest in the least significant bit. It oscillates between 0 and 1 and changes between each subsequent pair of numbers. The second least significant bit changes with smaller frequency. The change is made every 2 numbers. The third one changes even slower. We also see that the values here are bounded to 2 allowed possibilities, zeros and ones. And the idea of using sines and cosines follows the same scenario. The first positions related to highest frequencies are changing the fastest, then subsequent values are changing slower. Each of the positions in the positional embedding vectors are bounded between -1 and 1. Using periodic functions, we also ensure that the distance between any 2 time steps should be consistent across sentences with different lengths. We have the first part discussed. Let's move on. There are some more intellectual adventures on our way to understand transformer. The positional embedding is calculated for each token separately, but can be calculated in parallel, and is summed with a static word embedding of a given token, generating a representation that is now position aware. You might wonder why we sum those vectors instead of using concatenation. It seems that this way of representing positional embedding with the usage of the periodic functions, which provides regularities, we allow the model to separate positional information from the information about the meaning while processing the embeddings in subsequent steps. The calculated representation of each token is then fed into the encoder block. Here, the encoder is much more complex than in the case of vanilla recurrent neural network. In vanilla RNN, we have one hidden layer that learns the meaning of the whole sequence, while here we have a sequence of transformations, a multi-headed attention module, followed by add and norm layer, followed by a feed-forward network, followed by another add and norm layer. Let's discuss it step by step, starting with the multi-headed attention. I promise that after we understand multi-headed attention, the subsequent steps will be much easier to comprehend. You already know what feed-forward layers are, and add and norm are 2 very simple tricks. An encoder block takes position-aware embeddings representing the meanings of words and their positions as input and transforms each embedding into a new one, a modified embedding which is returned as the output. In other words, we can see the encoder as something that transforms one embedding into another, which is richer in information. Before we understand the multi-headed attention, or in the context of the encoder, more precisely multi-headed self-attention, let's describe the self-attention idea, focusing now only on the one head. Here we take an embedding as an input and produce a new embedding that is context-aware. The idea of self-attention is a small modification of the standard attention we discussed at the beginning of this lecture. In classic attention mechanism, we compare a given decoder representation with each of the encoder's representations to find which encoder states are the most important for us at a given time step, here from the Q1 vector perspective. The self-attention is a slight modification. Instead of calculating the attention between the decoder and encoder, we calculate the attention not between the modules, encoder and decoder, but only within a given module, here the encoder. And this requires some clarification. Why do we need to calculate the importance of the words limiting our context to the same sequence? When processing a sample input like Mary has a little lamp and enjoys spending time with it, why do we need to find out for a given token which tokens are important in the same sequence? This example is a good example to clarify that, because it uses the pronoun it. What does it refer to? What does it mean? In this slide, we can see some other example using the pronoun it. The animal crossed the street because it was too tired. Does it refer to the animal or maybe to the street? Being able to answer this question is important for us because we would like our embedding representing the word it to be meaningful. And here self-attention helps us. For each token in the sequence that enters the encoder, we calculate the similarity of its embedding with embeddings related to all tokens in the same sequence. In this picture, we can see the similarities calculated, for example, using dot products between the embedding related to the word it and all tokens in this sequence. When the similarity is high, the color is more intense. As we can see in this case, the most similar, the most important words in this case, from the perspective of the word it, are the and animal, on which we indeed should focus trying to generate the meaningful representation of the word it. And this is the general idea of the transformer architecture. We try to express the meaning of a given token, for example the word it, using the meanings of each token in the same sequence, and trying to identify those tokens that are more important to understand the meaning of a given word. It is helpful not only in the context of polysemic words like it, but trying to express the meaning of a given word using the meanings of all words in a given sequence may be always beneficial. Moreover, this way we can generate contextual embeddings, because the new representation of a given token is the mixture, some linear combination of the representations of the tokens in a sequence. But if you think about it for a while, there is some important problem. In general, the most similar, the most important word to it should be the it itself, because we also calculate the similarity between a given token and the token itself. And yeah, that's true. Now we need to dive deeper to understand the self-attention internals. Instead of comparing embeddings that are passed to our encoder, we transform those embeddings using three separate matrices, three separate transformations to produce three different vectors for each embedding. These vectors are called key, query, and value. The matrices producing keys, queries, and values are frequently referred to as WK, WQ, and WV, and the parameters stored in them are optimized during the training of the transformer model. Producing such three different representations for each token is the idea that is taken from the field of information retrieval. We can frame our problem here as an attempt to find the most relevant tokens in our sequence for a given special token called a query. If we use some web search engine, for example searching for some pictures of cats, we type some query, a cat. Then what the search engine does is the process of comparing the query with the labels of the images available. Those labels can be referred to as keys. If we manage to find the most relevant key to our query, we can return the image, the content assigned to a given key, which we call value. We can follow the same steps here in the context of self-attention. For each token in our input sequence passed to the encoder, we generate a query, a key, and a value vector out of a given embedding by multiplying the embedding vector by appropriate matrices. Then, trying to generate a new representation for a given token, let's say the first one, we use the query vector and compare the query vector to the keys assigned to all embeddings in the same sequence. As queries and keys are produced using different matrices, they will be different vectors, so that the similarity between the query of the word it and the key of the word it might be lower than the similarity between the word it and animal. Finally, we can construct new embeddings by using the weighted sum of the value vectors according to the similarities, thus the importances, attention weights calculated. We can even use the power of linear algebra to effectively calculate keys, queries, and values for each token in our input sequence at once. If we stack those tokens, those embeddings in subsequent rows, the result of multiplying this matrix by wk, wq, and wv will be another matrix where each row represents a key, a query, and a value of a given token. Trying to extract a key vector, a value vector, and a query vector for a given token, for instance, the third token, we simply extract the third rows of the generated matrices. For instance, the third row of the keys, or the third row of the queries, or the third row of the values. Let's discuss in a step-by-step manner how new representations are calculated using self-attention. The whole process of calculating a new richer representation of a given token Ti consists of 5 steps. First, we select the query vector assigned to the token Ti. Then, for every key assigned to the tokens in the sequence, we calculate the similarity between the query and a given key, using, for example, the dot product. Then, we divide the scores, the dot products, by the square root of the length of the key vector. Then, we calculate attention weights by applying softmax on those similarities. Finally, we calculate the new embedding for Ti as a weighted sum using attention weights over value vectors assigned to each token. We start with a set of tokens representing the encoder's input and the key, query, and value vectors produced for each of them. Assume that we want to generate a new representation of the word like. Let's choose its query vector, as this word will serve as our query at a given time step. Then we use the key assigned to each of the inputs and calculate the similarity between our query and a given key. We might use the dot product here for that purpose. We see that the similarity between our query and key 1 is equal to 96. The similarity between our query and key 2 is 108. And the similarity between our query and the key 3 is equal to 116. This way, we obtain information on how important each token is from the perspective of our query of the token like. However, these values are unbounded. We see that the most important token is the third one, NLB, because the dot product is the highest. However, it's not easy to interpret such value, as it might become anything from minus infinity to plus infinity. We will normalize those values, but first let's scale them by dividing them by the square root of the length of the key vector. This will help us in the subsequent step. Assuming that the key vector has 64 elements, the square root of its length is 8. Dividing each value by 8, we obtain 12, 13, and 14. These numbers are still uninterpretable, so let's process them using the softmax function. We obtain a set of numbers where each number falls between 0 and 1, and the sum of all values is always equal to 1. These are exactly the attention weights as described at the beginning of our lecture. Now we can discuss the need of dividing the dot products by the square root of the length of the key vector. Long vectors might produce large dot products, as they are sums of the products of the values at the corresponding positions of two vectors. The variability of those values might be quite high for those long vectors. If we calculate the softmax over the original similarities, the dot products, we can see that the attention weight related to the third position is really large and dominates the other tokens. Scaling those values by the square root of the length of the key vector, we obtained a softmax normalized vector which is not that dominated with this last key. The problem is not a result of large values per se, as we can see comparing the second and the third example, where in both images the three similarities differ only by 1. If this is the case, the softmax values calculated for those cases are the same. However, the difference of 1 is almost 10% of the value in the second image and about 1% of the value in the third image. It's much easier to produce a dot products which will vary a lot, like in this case, so that we introduce a normalization factor, the square root, to mitigate this problem. Having calculated attention weights, we can simply construct a new embedding vector, a new context vector T2, representing the meaning of the word like using a weighted sum over value vectors. This sum is weighted according to the attention weights calculated. And this procedure is the same as in the context of classical attention discussed at the beginning of our lecture. The only differences here are the scaling factors, dividing by the square root of the length of the key vector, and the idea of calculating attention over encoder's value only and not between an encoder and a decoder, which explains why we call it self-attention. The self term refers here to the same module. Please note a really important aspect of this approach. As we don't utilize recurrent connections, we can calculate a new representation for each token in parallel. We simply transform each input embedding into a triplet of a key, a query, and a vector, and then each token can be transformed into a new representation at the same time. We simply take its query vector and calculate the rest. And this highly increases the training speed. Moreover, using attention, we have an access to each encoder's state. In practice, we have some limitation on processing at most 512 states due to memory constraints. There is no vanishing information problem, as we observed in the case of vanilla RNNs and the last hidden state, which was dominated by the last tokens in a sequence. All those transformations can be calculated efficiently using matrices. We already showed that keys, queries, and values can be calculated at the same time for every token if we stack the input embeddings and transform them using transformation matrices. The resulting matrices can be directly used to calculate all the described processing steps using a single equation. If we transpose the key matrix representing keys so that the keys of a given token will be stored in columns, multiplying the matrix Q representing queries by key transposed, we obtain a new matrix, a matrix consisting of all dot products between all keys and queries. Then we can divide the values of that matrix by a scalar, the square root of the length of the key vector, and then apply the softmax over the rows of this matrix. Then we can utilize such attention matrix and multiply it by the values matrix. The resulting matrix will contain vectors that are new representations, new embeddings for each token in a sequence, and this will be stored in rows. Every token will have one row which will represent the new embedding. This approach is amazing, as we show that we only need attention to calculate new richer embeddings. We can use a sequence of matrix transformations to find the representations of all the embeddings at once. If we use some GPUs for that purpose, which are optimized to process matrices, we can generate new representations really quickly. But for now, let's get back to our story. As we now understand the idea of self-attention, we may introduce the idea of multi-head attention, or more precisely, in the context of the encoder, multi-head self-attention. The authors found out that instead of learning one set of transformations generating keys, queries, and values for each embedding, it would be reasonable to use multiple transformations. As the attention tries to find the importance of a given token in relation to another one, introducing multiple mechanisms like that might result in calculating various sets of keys, queries, and values, which will focus on different aspects of importance. They will look at the problem of estimating importance from various perspectives, and the authors call this idea multi-head attention. There are multiple attention mechanisms differing in the matrices learned to generate keys, queries, and values, because each matrix here is different. Each of these attention mechanisms will produce embeddings representing tokens, so that we have to join those representations together to form the final embedding. This is why we concatenate the output of the multi-head attention. An image from the Attention is All You Need paper represents the idea of multi-head attention. Here, in the context of the word it, multiple self-attention mechanisms are used so that they focus on various parts of our texts. And the final representations that are calculated here are then concatenated so that the resulting embedding will use various aspects of similarity. And yeah, finally, we calculated the outputs of the multi-head attention, which is the first step of processing in our encoder block. It's important to remember the general workflow here. The multi-head attention takes some embeddings sent to encoder, and for each input, for each embedding, it generates a new representation. Those representations can be produced in parallel. Now we can move on and describe the subsequent steps that process our embeddings even more. Fortunately, these are less complex. The add and norm layer consists of two operations. The first one is really simple and involves the usage of a residual connection, which sums the input of the multi-head attention with its output. Simply add the embedding being an input to the multi-head attention to its output, so the resulting vector will be more aware of the original input. Those residual connections are frequently visualized using arrows that bypass some modules like the multi-head attention here. Why this operation might be useful? Citing an interesting discussion we can find on Stack Overflow, the reason for having the residual connection in transformer is more technical than motivated by the architecture design. Residual connections mainly help mitigate the vanishing gradient problem. During the backpropagation, the signal gets multiplied by the derivative of the activation function. In the case of ReLU, it means that in approximately half of the cases, the gradient is zero. Without the residual connections, a large part of the training signal would get lost during backpropagation. Residual connection reduce effect because summation is linear with respect to derivative. So each residual block also gets a signal that is not affected by the vanishing gradient. The summation operation of residual connections form a path in the computation graphs where the gradient does not get lost. Initially, those residual connections were proposed for computer vision. If you want to learn more about it, you can read the paper Deep Residual Learning for Image Recognition. I have added the link at the bottom of the slide. The next operation, called here norm, is a simple normalization of the resulting vector. As the sum of vectors might result in big values at some vector's position, it might be helpful to normalize those values using a layer norm approach. To use it, we take the output of a given layer, calculate the mean value and standard deviation, and then normalize each output's value by subtracting the mean and dividing by the standard deviation. As a result, the vector we produce will contain small values dispersed around zero. You can find more on this topic in a paper entitled Layer Normalization, the link to which you can find on this slide. And that's all. This step is much simpler than the multi-headed attention. The output of add and norm is then fed into a feed-forward network consisting of two dense layers represented using those W matrices and biases, with a nonlinearity applied in between. The max operation represents the ReLU activation function. Then, because the values of the resulting embeddings are not bounded, we apply add and norm one more time, producing the output of the encoder block, of the one encoder block. The described set of transformations, multi-head attention, add and norm, feed-forward networks, all compose a single encoder block. This whole block processes tokens in parallel. However, Transformer proposes to use a stack of encoders. For example, to use a stack of 6 encoders blocks. Each of these encoders has their own matrices. So when dealing with the self-attention mechanisms, we introduce multiple different matrices, let's say horizontally, when introducing multiple heads in one encoder block. But we also introduce multiple matrices vertically, as each encoder block uses their own transformations, producing keys, vectors, and queries. And these are different transformations. So there's a lot of computation here, but the possibility of doing it in parallel allows us to use them efficiently. Finally, the output of the top-level encoder is the final representation of our input sequence. And we can move on to discussing the decoder part of the transformer architecture. Fortunately, the decoder is quite similar to the encoder. The decoder also consists of a stack of decoder blocks. Here, each decoder block is aware of the representations produced by the top-level encoder block to generate the sequence of outputs. The decoder works in an autoregressive way, so that the outputs produced are then fed as an input to the decoder. This way, the decoder can produce next token knowing which tokens were produced before. These decoder inputs are presented in the image provided by the authors of the paper. However, let's discuss now the internals of a single decoder block. If we compare an encoder block and a decoder block, these are quite similar. There is an additional step in the decoder part called masked multi-head attention, and the, let's say, regular multi-head attention is also modified a little bit. This small modification is discussed on this slide. As we can see in this picture, the two incoming arrows come from an external source. In fact, keys and values into multi-head attention provided in the decoder are delivered by the encoder, while the query is delivered by the decoder. And this is exactly the same scenario as we discussed in the context of encoder-decoder architectures. Here, we also have a query coming from the decoder, and we evaluate the importance of encoder outputs from the perspective of the current decoding step. Now let's discuss the idea of masked multi-head attention. The encoder allows us to process each token in parallel in the context of a single encoder block. The representations from the lower levels, either original static embeddings or the embeddings produced by a lower level encoder, were all available so that the encoder could generate the new representation for each token in parallel. In the context of the decoder and the training phase, we could also apply some parallelism. The decoder's stack goal is to produce a sequence of outputs, for example, the translation of a given sentence in English into German. We know what the expected output sequence is during the training process. At each time step, the decoder should be able to predict the next word given the encoder information and the information about already generated words. At the first step, the decoder might obtain the beginning of sequence token as an input, which should encourage it to produce the most probable first token in the translation, here the word lubię. On this slide, we want to translate a given input sentence I like NLP into Polish, which should be lubię NLP. Then, knowing that we produced the word lubię, which was the first token in our output sequence, we know it because we already processed the BOS token, we should learn to predict the token NLP based on that information about the whole sequence. Finally, if the input to our decoder is the whole BOS lubię NLP, The output should produce EOS, end of sequence, marking the end of the generated translation. If you look at the inputs and outputs sent to the decoder, you can see that each input token is shifted right. The first output of the decoder is the second input of it. The second output of the decoder is the third input of it, and so on. This is the story of those shifted right outputs visualized here in this picture. So maybe we could parallelize each of the decoding steps during training. We know the sequence that should be produced at a given time step and what is the expected continuation, like the EOS token after the BOS, Lubian NLP. Maybe we could even use some multi-head attention as described in the context of the encoder module. That might be a good idea, however, we have to be really careful. During the training phase, we know all the inputs sent to the decoder so that we know what the expected translation should be. If we apply the self-attention mechanism on this, we obtain the attention matrix, where we can observe that from the perspective of the first token, the BOS token, all other tokens have some importance calculated. However, if we see the whole sequence, we see what is the next expected token in that sequence. That's really bad because this is cheating. Instead of learning what the next token should be, we simply have it provided. We see that after the word begin of sequence, there is the word Lubian. We need to prevent such a case. We need to make the decoder unable to see what are the future tokens when calculating the attention matrix, so that the token begin of sequence in the first step is only aware of itself. Then in subsequent steps, the word Lubian might be aware of itself and the previous token BOS, and finally the token NLP should be aware of both BOS and Lubian. How can we achieve it? When we calculate the attention matrix, we calculate the dot product similarity between the tokens in our decoder. Then we scale them by dividing by the square root of the key's vector length. At this moment, we can introduce an additional operation. We might simply add a new so-called attention mask to the similarity matrix. The matrix is filled with minus infinity values over the diagonal, and the rest of the values are set to 0. If we add those two matrices together, the values on the future positions become so small that the softmax applied to it assigns them the value equal to 0. As we can see here, after utilizing the attention mask, the whole information available for the token BOS at the first step of decoding comes from the word itself. It does not have an access to the future words Lubian and NLP. So when we build the context vectors, the value vectors assigned to Lubian and NLP won't be used at all because these will be multiplied by zeros. The same applies to subsequent steps. The word Lubian now sees itself and the BOS token, while the word NLP sees the whole sequence. This small modification results in the masked multi-head attention. The remaining building blocks of the decoder were already discussed in this lecture. The output of the final decoder is processed by a linear, a dense layer, and the softmax, which generates the probability distribution over all tokens in our vocabulary. We choose the output and send it to the decoder to process a subsequent step. We have to remember that while using a trained model, the encoder might work in parallel, transforming all tokens at once. However, the decoder needs to produce tokens in a sequence. In order to produce the third token, it needs to produce the two first ones before. So the ability to parallelize can be used in the context of the decoder only during the training phase. The transformer architecture is extremely efficient. We can parallelize our training so that it is possible to train large models quickly. The authors of the Attention is All You Need paper built two kinds of transformers, the base one and the big one, and evaluated them on the machine translation task. The base transformer consists of the stack of 6 encoder blocks and 6 decoder blocks, using the embeddings of the size equal to 512. These are produced using 8 attention heads. The dimensionality of the inner layer feed-forward is set to 2048, and the size of the keys vector is set to 64. The final model consists of 65 million parameters. In the case of the big model, we have twice as many attention heads, which results in the embedding vectors of size 1024. The inner layer is also bigger, consisting of 4096 positions. The final model consists of over 200 million parameters. Those models were trained on the datasets consisting of pairs of sentences expressed in English and German and English and French. The training time was equal to 12 hours in the case of the base model and 3.5 days in the case of the big model. They used 8 NVIDIA P100 GPUs for that purpose. The transformer architecture has many pros, and as compared to previously used models, it can model long-range dependencies using attention. The transformer can encode the positional information efficiently using positional embeddings, and, what is extremely important, the transformer allows us to process sequences in parallel. However, there is one drawback here. If we look at the complexity of several approaches like self-attention, recurrent neural networks, and convolutional networks, we can see that the self-attention is more efficient as it can process the whole sequence at once. In contrast, the RNN network has to process sequences element after element. Moreover, the maximum path between a given two tokens is 1, as the self-attention mechanism compares each token pair regardless of their distance in the original text. However, the complexity per layer in the self-attention scales quadratically with the input sequence size, because for each token we need to treat that token as a query and calculate the attention weights comparing it with all tokens available. This allows us to construct the attention matrix, but also it generates high memory usage. In practice, we frequently observe a limitation in which the transformer model can process only 512 tokens at once. The transformer architecture was a huge success. Soon after the publication of Attention is All You Need, the idea of using an encoder-decoder architecture based on self-attention was used not only to solve machine translation tasks, but also other tasks. The authors of the T5 model, which was provided by Google and introduced in the Exploring the Limits of Transfer Learning with a Unified Text-to-Text Transformer paper, showed that we can even use the transformer architecture to train a model which can solve various tasks at once. The T5 model can even solve classification and regression tasks, transforming them into sequence-to-sequence scenario. In this picture, we can see some sample inputs sent to T5 and the output it produces. If we want to translate from English to German, we simply start our input with an appropriate prefix, like translate English to German, that is good. And the T5 produces the translation, here, das ist gut. If we want to perform classification to determine, for example, whether a given sentence is correct or not, we can use the following prompt to obtain a class telling us whether a given sentence is acceptable or not. Note that here the classification is solved by producing a sequence representing the label of the class. Similarly, we can calculate the semantic similarity between two sentences. The example prompt here returns a number which represents the similarity score between two sentences. And this is a kind of a regression task transformed into a sequence-to-sequence problem because we answered that question generating a sequence of characters. Moreover, we see an example of the text summarization process in which we generate shorter representation of a given text. The T5 model was a huge success. Recently, in 2022, a continuation of this work called FLAN T5 was also proposed by Google. In the paper Scaling Instruction Fine-Tuned Language Models, they use a similar idea to teach a model to solve almost 2,000 tasks. And this slide concludes our story about the transformer. During the labs, we will use T5 models for various tasks. Thank you and see you later.